the unit circle and the 6 trig functions.
Okay.
And starting to do more, we just started graphing today.
Okay.
But for now, I want to do more problems with, or to start, I want to do some problems with just conversions and the 6 trig functions.
Okay. Go ahead. I would think that that first session we had, not the last one, but the very first one we had on the unit circle would really be coming in handy at this point in time.
Yeah, quite a bit.
Okay. What other stuff you want to cover?
All right.
Can you verbalize them all? When you said you're getting into graphs, are some of these questions where they give you the graph and they ask you questions about it?
A few of them are, so I'm going to have to send you some in a little bit, but
Okay.
I think I'm good for now. So the first one is find the cosine of pi over 4.
Any particular method or just find it?
Just evaluate the following and give exact answers.
Okay. By exact answers, they mean radical signs.
Right. No
Okay.
distance.
So you're probably still at a stage where you need to convert these to degrees in order to be able to do this problem. Right?
Yeah.
I'm going to draw my 30-60 because all of these you're going to get the, what's the dimension opposite the 30?
2.
They're called my unit triangles.
Right.
Always one opposite the smallest angle.
Okay.
And that gets you started. And then this is square root of 3 and this is 2. And if I look at the 45, 45, what's opposite the 45?
1.
And opposite the other 45?
1.
And the hypotenuse?
Square root of 2.
There you go. Okay. So let's first of all convert this pi over 4 radians to degrees. And you can do this however you want. In other words, you can multiply it by the conversion factor. To me, that's kind of the hard way. We know that the answer times 4 is equal to 180. So if you divide 180 by 4, as long as the numerator is just pi, you'll come up with the conversion.
Oh, so just substitute pi for 180?
Well, no, here, let's go through these again. To me, this makes things so much simpler that it's a crime almost not to do it this way. And the other one is pi over 6. Okay? That's equal to 90 degrees because 90 times 2 is 180. This one's equal to 60 degrees because 60 times 3 is 180. So pi over 4 has to be 45 degrees. And I got that by dividing 180 by 4. So what's pi over 6?
30 degrees?
Yeah. And to me, that is a far simpler method of using it whenever your numerator is just pi.
Right.
Instead of going pi over 4 times the conversion factor, which is 180 over pi, notice that what I'm really doing is dividing 4 into 180.
Right.
Just doing it in kind of a shorthand method. And once you memorize these 4, and if they're not hard to memorize because of that 180 number, but once you do, it'll make your conversion to radians all that much faster. So that you'll get to a point where you can do all your trig problems in radians without converting to degrees.
Okay.
But most immediately, we're going to convert to degrees for the moment. So this is 45 degrees. What's cosine of 45 degrees?
Root 2 over 2.
Correct. Now notice that that's the same as my triangle, which is 1 over root 2 rationalized.
Right.
Some school systems will actually give this triangle in the following manner. They'll make it 2, 2, and, they'll make it root 2, and 2.
Oh, okay, right.
You see why? In other words, that's the same as, it's the same ratios. It's the ratios that matter. And if I call that root 2 and this root 2 and that 2, that's the same as my other triangle. It's just not a unit triangle.
Right.
And the advantage of using this is that it comes ready rationalized when you're doing cosines and sines.
Right.
However, if I said, what's the secant of 45 degrees? Now you're going to say 2 over root 2, which I then have to rationalize. Whereas, had I left it as a unit, then secant never has to be rationalized. And still have to rationalize sine and cosine, but not secant and cosine. So, the best advice I've heard yet is one of his students told him, don't rationalize anything. If it's 1 over root 2, leave it that way.
Right.
And I love that advice. It eliminates this whole problem. And to me, this is easier things to remember, these two triangles, than if this was root 2, and 2. All right, what's next?
So the next one says find the point on the unit circle that corresponds to theta equals 4 pi over 3.
Okay, so what we have to solve here is the cosine of 4 pi over 3 and the sine of 4 pi over 3. Remember the point that is x comma y. X is the cosine of that angle. Y is the sine of that angle.
Right.
In order to find that xy coordinate, we need to answer that and that. So let's use our unit circle. I'm going to draw it right over here. And which quadrant is that angle in?
Quadrant 2.
Okay, here's another easy way. If pi over 3 is 60, what's 4 pi over 3?
Uh, 240.
Okay, what quadrant's 240 in?
Quadrant 3.
Okay. Notice that once you learn these 4 here, then all of the difficult ones, like 4 pi over 3 or 7 pi over 6, can all be done rather quickly. 4 pi over 3 is just 4 times 60. 7 pi over 6 is 7 times 30, and so forth and so on.
Okay.
And we know that it's all students take calculus, and in quadrant 3 it's theta minus 180, or if I want to work in radians, it's theta minus pi. Remember, 180 is equal to pi.
Right.
So let's work this problem in radians. What is the equivalent, and we'll do cosine. What is the equivalent first quadrant angle?
Negative 5 pi over 6.
No. We're going to use this theta minus pi, not pi minus theta. Theta
Okay.
is 4 pi over 3, right?
Right, okay, I was looking at
4
pi.
pi over 3 minus pi is what?
Pi over 3.
Okay, so in parentheses, I'm putting what its equivalent first quadrant angle is. Now, go up from your triangles and tell me what cosine of pi over 3 is.
Adjacent height. Well, 1/2.
Okay, and what is its plus or minus sign?
Negative.
Good. Now let's do the same thing for sine of 4 pi over 3. Its equivalent is clearly the same thing. What's the sine of 60 degrees?
Root 3 over 2. Negative root 3 over 2. For the sine of 4 pi over 3.
Okay, so if we go down to this unit circle here, I don't want to mess up everything, but here I'll draw it really tight. There's my unit circle. The angle they're talking about is 240 degrees, which puts it right about there. And this XY point that I just put the X through, coordinates are minus 1/2. The first coordinate is cosine of the angle. Second coordinate is minus root 3 over 2. That's the Y coordinate. And this really is what they want you to memorize on the unit circle. In other words, they want you to give the X and Y coordinates for each of these, all of these angles that are multiples of 30 and 45. So what you really have to do to be able to fill out the unit circle is you got to be able to do a lot of sines and cosines. Or I should put that in opposite order, cosines and sines, because the X coordinate is cosine.
Okay.
Okay? What's the next one?
Same kind of problem, but theta equals 15 pi over 2.
Now, notice in that last problem, we did everything in radians until you got to pi over 3, right?
Right.
And then you knew that was 60 degrees, so you were able to read this triangle. So, in a sense, you did, at some level, convert it to degrees. But you could also label this triangle. I could label, instead of 30, I could label that pi over 6. And instead of 60, I could label it pi over 3.
Right.
Okay. So 15 pi over 2. This is a huge angle that's outside the unit circle, right? In other words, the circle goes 0 to 2 pi. This is 7.5 pi. So how many unit circles do I have to subtract to get this thing into the unit circle? And that's kind of the way you want to look at it. Subtract or add. In other words, I want to convert this to an angle that is in less than 2 pi.
Okay.
How do I do it?
Subtract 13 over 2.
Well, you have to subtract in multiples of 2 pi. So I could subtract 2 pi, 4 pi, 6 pi, or 8 pi. Which one do I want to subtract?
8 pi.
You know, that would be 16 pi over 2, and I'd end up with a negative angle. Until we have to, let's not get negative angle.
Okay.
Okay? So I can really only subtract 6 pi. which is 12 pi over 2.
Okay.
And what that gives me is 3 pi over 2. So the problem they ask is the same as theta being 3 pi over 2. Now, what angle is that?
270 degrees.
So where is it on the unit circle?
You mean the point?
Yeah, it's right there, is it not?
Yes.
What are the coordinates on that? You don't even need to do the math here. So
0, 1.
yeah, 0 comma minus 1. In other words, the quadrangles, anything that's a multiple of 90 is a quadrangle.
Right.
Quadrangles are actually easier to do. You don't even have to know what the sine and cosine are, just because they lie on these axes. You knew what the coordinates were before you even thought about it. But the thing is that they are so worthwhile is you now can look at these coordinates and know what is the cosine of 270?
0.
What's the sine of 270?
-1.
Correct.
Okay.
All right. Erase.
So,
I need a bigger unit circle is what I need. I don't want to erase information. And the key information being up here. It's easy to get these backwards. Remember that in the second quadrant it's 180 minus theta. In the third quadrant it's theta minus 180. And the way to remember this is it's always supplemental to the angle. If I told you theta was 150, we know that equivalent first quadrant angle is whatever is supplemental to 150. And you get that by 180 minus that.
okay.
Okay? Go ahead and call you and have you turn your audio setting to telephone.
Okay.
Okay,
Amazing. Amazing how the absence of noise is soothing. I guess it's like beating your head against the wall because it feels so good when you stop. Okay. What else you got?
So this next one, it's kind of a weird problem. It's name all the values of theta on the unit circle if tangent of theta equals -1.
What two quadrants might that be in?
2 and 4.
Correct. Has to be. Because tangents are always positive in quadrant 1 and they're always positive in quadrant 3. So which angle are we looking at? Is it 30, 45, or 60, where the tangent's equal to 1? Ignore the negative sign for the moment. We have to figure out what theta is, what the equivalent first quadrant theta is. Examine the tangent of all three of these angles and tell me which one is equal to 1.
45.
Okay, so we know that the angle is 45 degrees, but it's the angle, we need a second and a fourth quadrant angle that are the equivalent to 45 degrees. So what's the second quadrant going to be? And you can do this straight algebraically. In other words, I got 180 minus 45, 180 minus the angle we're looking for, which I will call x, equals 45. Solve that equation, you get an x of 135. So the second quadrant angle of 135 has an equivalent first quadrant angle of 45. It's also in the fourth quadrant. And in the fourth quadrant, here's the formula. 360 minus the angle we're looking for equals 45. What does x come out to be?
315 degrees.
There's your two angles. In other words, this is pretty much the other process in reverse. Okay? In other words, the other process, they would have said, what's the tangent of 135 degrees? We would have figured out its equivalent first quadrant angle, read it off the triangle, figure out whether the sine is plus or minus. Notice that this is going in exact reverse. It tells you the result, minus 1, and then we have to figure out what quadrants that must be. And if it's second and fourth, then we have to come up with angles whose equivalent first quadrant angle is 45 degrees. And you can do the whole thing algebraically just using these formulas. What might be a little confusing is that they're not giving you theta. They're giving you the reference. When I say the equivalent of the first quadrant, that's also called the reference angle. Your teacher probably does these slightly different. He probably uses the reference angle extensively, whereas I call everything what is its equivalent first quadrant angle. Same, we're meaning the same thing using different terminology. To me, it's easier to think of everything as having an equivalent first quadrant angle, because I know how to do all the first quadrants. The first quadrants are easy just looking at these two triangles. As opposed to thinking reference angles, which is always the angle made with the x-axis regardless of which quadrant you're in. Okay. You follow me on that logic? I'm not sure I explained it.
No, yeah.
Okay, good. I was going to say, if not, let's do another one similar to that, and we'll go through the exact logic again. Let me get rid of all of this and leave what else is there. Okay, go ahead.
All right. Find the exact values of sine, cosine, and cosecant given secant of theta equals 3, comma 3 pi over 2.
All right. I'm going to move down a page here because now we're getting into kind of the most common problem in trig. And that is where they give you one trig value and they tell you which quadrant it's in. This is what you were trying to verbalize.
Yeah.
And probably less than 2 pi.
Yes.
Okay? So there's a really easy way to do all of these problems. Step 1, figure out what quadrant that is.
Quadrant 4.
Yeah. I'm not even sure that's step 1. That might be step 3. Usually my step 1 is draw a triangle and label theta. That's step 1 in my book. Now dimension as much of that triangle as you can. When I say a triangle, I meant a right triangle. And it's important to label theta because theta could be down here or theta could be up here. So labeling theta is critical. Now, what dimensions can you give me on this triangle? Do you know the hypotenuse? They told you that the secant of theta was 3, which is the same as 3 over 1.
Right.
So the hypotenuse is 3.
Okay.
Which side is 1?
The side opposite of theta.
Nope. If that was 1, then the sine of theta would be 1/3. I'm sorry, the cosine of theta would be here. It has to be this one here. Because if the two sides are this way, then the cosine of theta is 1/3, right? Which makes the secant of theta 3 over 1.
Okay.
In other words, whatever trig function they give you allows you to fully dimension the triangle. If that's 3 and that's 1, what's this side opposite theta? You want to get so you can do these pretty fast. When you have the hypotenuse and one short side, the other short side is always the square root of the hypotenuse squared minus the other short side squared. And that's what I mean by doing them fast, as opposed to starting with the Pythagorean theorem and doing all the algebra to solve for A.
Right.
You have to solve so many right triangles that this is quicker way to do it. And if I'm solving for the hypotenuse, then it's always this.
Right.
So this is when you're solving for the hypotenuse. This is when you're solving for either short side, where B is the other short side. So 2 root 2, exactly.
Okay.
But with trig, because you have so many problems like this, you really want to do it in a fast manner where you can put the third dimension on this triangle down quickly.
Okay.
Okay, especially on tests. And this is a problem you get a lot on tests. So now we know the triangle and we know the quadrant. It's fourth quadrant based on that. So they wanted the sine of theta, they wanted the cosine of theta, and what else did they want? Cosecant?
Yeah, cosecant.
Notice I'm going to be able to answer this without ever knowing what theta was. What's the sine of theta?
1 over 2 root 2.
No?
Sorry, 1/3.
No? Socatoa.
Right. Sorry. 2 root 2 over 3.
Okay. What's the cosine of theta? Hold on, let me back up. What's the plus or minus sign on the sine of theta in the fourth quadrant?
Negative.
Okay. And now what's the cosine of theta? Based on this big triangle we're looking at.
Positive 1/3.
Okay. And what's the cosecant of theta?
Negative 3 over 2 root 2.
Good. Now can you kind of understand why that teacher makes a lot of sense? That he doesn't want everybody spending all their time rationalizing denominators? This would be what I would like as an answer, but you're 90% of the teachers are going to want you to rationalize everything. So for our purposes, you and me, let's just assume you know how to rationalize stuff, and we can live with this answer. And if you're taking a test, go ahead and rationalize it if you have to, if you will not accept an irrational denominator like this.
Okay.
Notice the plus or minus sign is always the same as its reciprocal, never different. If sine was negative in the fourth, cosecant is also negative in the fourth.
Okay.
Okay? All right, let's do another one of these. These are really key because this is almost like the quintessential trig problem.
Okay.
Where they give you exactly one trig function. Remember, we never did solve for theta. Didn't have to.
Right.
That's what's cool about those problems, is you can get the other 6 trig functions without ever even knowing what theta is. I can make one up if you want.
Yeah, I don't have any more on my
Let me make one up.
Thank you.
I'm going to say the tangent of theta is 7/2. And that theta is same thing, greater than or equal to 270, less than or equal to 360. I'll use degrees. What are the sine of theta and the cosine of theta and the cotan of theta equal to? Step 1 is what?
Make a triangle.
Yeah.
And
And this is what maybe is different. I'm not sure your teacher necessarily teaches this as the way to do it. There's a harder way to do it. And that is to go to the unit circle and draw this triangle in the third quadrant and do it that way. To me, that's much harder. This way is lickety-split easy. What can I label on this triangle at the moment?
the opposite side is 7, and then the adjacent side is 2.
Making the hypotenuse remember it's
root 53.
Yep.
Okay.
They always start out root, square root up. Sometimes it's a whole number and that'll convert to an integer, but most of the time it doesn't. And I don't think I can simplify that. I don't believe that. I think that's prime. So what is the sine of theta?
7 over root 53.
It's plus or minus sign?
Negative.
And to me, that's the easiest way to do it, is to figure out the number first and then the plus or minus sign. So when I'm doing these problems with you, I'm always going to ask that last. You can give it to me first if you know it, but I don't know. You know, there's certain advantages in always doing something exactly the same way. What's cosine of theta?
2 over root 53.
And what is its plus or minus sign?
Positive.
And what's cotangent of theta?
2 sevenths.
What's its plus or minus sign?
Negative.
Yeah, I screwed up here, didn't I?
A little bit.
I meant to put this in the third quadrant. I put it in the fourth quadrant. Here, let me change it real quick. Because the tangent can't be positive in the fourth quadrant. In other words, the conditions I gave you were impossible. Actually, let me leave it like it is. Let me leave it the easiest way to fix that problem.
Make the tangent negative?
Yeah, is we'll just make this a negative. Because even if it's negative, the first step is to draw this triangle. In other words, you're basically going to ignore the negative sign until you get to these problems. And in fact, we're never going to look at the negative sign, except maybe when we do cotangent of theta, we know it's the reciprocal of tangent. We're looking at the tangent, so it has to be negative also. But in terms of, I'm glad this came up, because they may give you a negative number to start with, and that might throw you off a little bit, because whenever you're looking at triangles, everything's positive, right? That's okay. You don't need to pay attention to the negative sign, especially if they tell you what quadrant it's in. Now, they won't necessarily always tell you the quadrant or give it to you like this. What they might say is the following. The tangent is -7/2, and the cosine of theta is greater than 0. That's enough information to identify the quadrant.
Right, so then you can...
That can only be the fourth quadrant. Can't be the first, can't be the second, because cosine's negative in the second. Can't be the third, because tangent's positive in the third. So it has to be the fourth. So they won't always tell you theta is between a couple angles, but they'll give you enough information that you can identify that as fourth quadrant. And you have to do this at some point. I don't like doing it as step one because so many people have difficulty remembering that ultimately they got to draw this triangle and label theta.
Okay.
So if I wanted to know what theta was here, how could I solve for it? Using your calculator.
You take an inverse tangent, right?
Of
7/2, or -7/2.
Yeah, you do -7/2, and what it's going to give you is a negative first quadrant angle, which actually is a fourth quadrant angle, right?
Right.
And if you were to put that in your calculator, even if you did inverse tan of 7/2, it's going to give you the angle, and then you got to convert it to a fourth quadrant angle. But you'll get it quicker if you have your calculator in front of you. Go ahead and put in inverse tan of -7/2, and it'll give you a negative angle that's less than 90 degrees. If you have it in front of you, you don't need to go get it, but...
Yeah, no, I have it.
Okay.
It's negative 74 degrees.
Yeah. That's a fourth quadrant angle. And that's the way it'll always give it to you. In other words, if you take inverse tangent of a positive number, it's going to give you the first quadrant only. If you take inverse tangent of a negative number, it's going to give you a negative first quadrant angle only. That'll be in the fourth quadrant. In other words, it's never going to give you, notice that tangent's also negative in the second quadrant. But your calculator didn't give you that angle, did it? The second quadrant angle would be 106 degrees. In other words, if you put in a tangent of 106 degrees into your calculator, it'll give you -7/2 or something close, because you've obviously rounded off some of these. So you got to be a little careful. When you're doing inverse trig functions, it's only giving you the principal quadrants. So sine, it's going to give you first and fourth. Tangent, it's going to give you first and fourth. Cosine, it's going to give you first and second. If you do the inverse cosine of a positive number, it gives you the first quadrant. If you do the inverse cosine of a negative number, it gives you the second quadrant angle. Always.
Okay.
So it doesn't give you all of the angles in the unit circle where the statement is true. It only gives you from two quadrants. Remember that when we did inverse, you have to restrict the domain of the original function, and that's why you end up with only first and fourth for sine and tangent in your calculator.
Okay.
So these problems, whenever they give you a value, that allows you to dimension two sides of the triangle. And then you always use the Pythagorean theorem to get the third. And then you just read off the answers from the three dimensions on whatever trig functions you have. Given one trig function, you can come up with the other five if you know the quadrant. Okay, what else you got?
So this next one is graphing.
Okay.
It says use transformations to graph y equals -3 sine of x plus pi over 2, all in parentheses.
I love it. Somebody finally is treating these as normal transformations. Most trig does not do that. Most trig will introduce this thing and they'll call it the sinusoid equation. And they'll go through what each variable does or what each number does. Well, that's one way to look at it, but the way that you've been taught for 3 years is transformations. What's the negative sign? What kind of transformation is that?
Reflection over the x-axis.
What's the 3?
Vertical stretch.
What's the pi over 2?
A horizontal shift.
Which way?
To the left.
Okay. Now, what trig does is calls this amplitude, calls this phase shift. Anything that would have been added like that is vertical shift. And you can have a multiplier of the x. Let's say I put a 2 in there. That's horizontal shrink. In other words, this thing they call the sinusoid equation, which has a standard format of this. Tell me if this is your standard. Your standard actually might be a little different. There are actually 3 different standards depending on the school district you're in. I believe this is the one you guys use.
I don't even think we've done that yet.
Oh, you haven't even gotten to it yet. Okay,
No.
so their way of introducing it to you is by relating it as a transformation, which I love. That's the way everybody should be introduced to sinusoid equations. This is a sinusoid equation. This equation describes the motion of an awful lot of things, from the tides to somebody's breathing to a spring going back and forth on a weight attached to it. Anything that is periodic in behavior, to a Ferris wheel going around and around, to somebody swinging on a rope out over a lake and back. Anything that has a periodicity to it, music, you can end up writing a sinusoid equation to reflect that action. Okay? For example, my basic sinusoid, or my basic sine of x, well, that just means a is 1, b is 1, c is 0, and d is 0. Well, that has a periodicity to it. It just repeats. Just like a Ferris wheel would keep turning as many times as the operator sets it to go around. Just like the tides go in and out at regular intervals. Your breathing generally is regular intervals. So your lungs are holding that much air after you've breathed in. You expel all the air and they're holding that much air when you breathe out.
Right.
So this sinusoid equation is really an important part of the next part of trig that you're going to get into, assuming they get straight into it. And the one objection I've always had to the way they teach trig is they call all of these things different things. You know, amplitude, B is related to the period, instead of what they've been calling with polynomials all along, which is vertical stretch, horizontal shrink, horizontal shift, and vertical shift.
Right.
All right. So, did you have, we've got another 8 minutes. What else you got? Without getting into the sinusoid function. And although I don't mind getting you a little bit ahead of where you're at in class, that's got to make it a little bit easier to absorb the information when your teacher goes over it.
Yeah, the first lesson you gave with the little the tips about the unit circle have really helped.
Yeah, no, I knew it would. I almost feel like sending an email student out to all my trig students saying, please schedule a session before you get through the unit circle, because it's vital before you go anywhere beyond that to be able to know how to get, you know, the sine of 225 degrees.
Right.
All right. So what else you got for tonight?
So this is going with linear and angular speed,
Okay.
which is incredibly confusing because I just finished doing the same exact thing in physics with different equations.
Well, the whole key with angular and linear speed, William, is units.
Right.
Okay? And here's what I mean by units. Let's just go, I'm going to make one up here because I don't want to get bogged down spending 3 minutes how to convert it. Let's say the most common question is somebody's got a vehicle and the vehicle has wheels that are 12 inches in radius. And they go around 10 revolutions per minute. That's angular speed, 10 revolutions per minute. And we want to know how fast this vehicle will move down the road. That's linear speed. Okay? So, how do I convert it? Well, let's start with the angular speed. And I want linear speed in miles per hour. So way over here on the right, I need to produce miles per hour. Okay? So I got to figure out how to convert everything. Well, let's deal with the hard part first. Let's figure out radians. What's the radian per revolution conversion factor?
2 pi.
Okay, so is it 1 over 2 pi or 2 pi over 1 in this case?
1 over 2 pi.
No, because that would be 1 revolution per 2 pi radians, which is true, but it doesn't get rid of revolutions. I've got to make this conversion factor. I can use the reciprocal, is always as factual as the original. And what I want to write is 2 pi radians over 1 revolution. And the reason I want to write it that way is because I know I got to lose revolutions. I don't have revolutions in my final answer. I got to lose both revolutions and minutes. So let's start with 2 pi radians over 1 revolution. That gets rid of that. Now, I've got to somehow get the numerator to be in miles. or a length? Well, here's the hard conversion, the one that everybody wants to forget. And that is 1 radius per 1 radian. I guess I need to spell it out here, huh? In other words, rad doesn't do it. That's what the definition of a radian is it's a radius. So in this case here, our wheels have a 12-inch radius. So 12 inches per 1 radian. With me?
Yeah.
That's going to cancel my radians. Now, at least I got everything in, right now I'm in inches per minute. Well, it's easy enough to convert inches to miles. I've got 1 foot per 12 inches. Again, it could be 12 inches per 1 foot, but it doesn't work if I do that here. I got to have the 12 in the denominator. Gets rid of my inches. Now I got feet in the numerator. Well, I know that there's 1 mile per 50 to 80 feet. And now I got rid of the feet, and I finally got miles in the numerator. I still got minutes in the denominator, so I need one more conversion factor, which is 60 minutes per 1 hour. That minutes cancels with this minutes over here. And now I've got miles per hour, and all I have to do is multiply 10 times 2 pi times 12, divide by 12, divide by 50 to 80, multiply by 60. And you have your answer in miles per hour. Okay? So these problems about angular speed and linear speed are always going to be done exactly like this. It's just that sometimes they're going to want the final answer. Sometimes they give you the miles per hour and they want to know what the radius of the wheel is. But it doesn't really matter what they're asking for. The problem comes down to getting your units to all cancel. And the reason that comes down to that is so you'll know whether to put 2 pi over 1 or 1 over 2 pi, and it's going to make a difference. So you have to make sure your units cancel out. We worked with some of these before, and I noticed that the ones they gave you, you were always solving for most of them you were solving for the radius of the wheel, and they told you that 10 revolutions per minute converted to 40 miles per hour, what's the radius of the wheel? Well, that just means your variable is the middle term here. You still have to get all the units to cancel. It's just instead of 12, it's x that we're solving for, or r. Okay? And when we have a little bit more time, we can do some more of those if you need to. They're definitely challenging, but they're not really challenging if you know how to do the original problem, which is where they give you the revolutions per minute and they give you the radius. Then do it exactly the way I did this. And if they give you some other, right now they've given us 2 variables, well, maybe they'll give you revolutions per minute and miles per hour and ask you to solve, well, the only thing to really solve for is radius. That's why all of those other problems you were solving for radius, because we're never solving for this or this or this or that. Those are all conversion factors. Maybe they'll give you the radius and miles per hour and they want to know what the angular speed is. So this would become x that you'd be solving for. So you can do it. You're always just going to have one variable. It's just a question of where it's at. Is it on the left side of the equation, or is it on the right side of the equation?
Right.
But once you
Okay.
once you determine that, then it just becomes an algebra problem. Just always work the problem based on units. All right, William, I will talk to you next time.
Okay, great. Thank you very much, Mr. Karen. Have a good night.
All right, you too.